Hi all, let us tackle two more equilibrium constants, Ka and Kb, which stand for the acidity constant and basicity constant respectively. In the previous video we discussed Kw, the equilibrium constant for autoionization of water. For this video we're going to look at two very important equilibrium constants, Ka and Kb. Ka is the simply acidity constant. Basically tells you how strong an acid is. Right now we're going to look at the strong acids. Okay, let's pick up a strong acid. Let's pick up nitric acid, HNO3. We're going to consider it aqueous. Okay, it's going to dissolve in water. We have water. We'll consider that liquid. And yeah, when you dissolve this in water, the ions are going to break apart. And the H plus is going to be picked up by a water molecule to turn into H3O plus aqueous. And, oh, the NO3 now is by itself, and we know that from the polyatomic ion unit, nitrate aqueous. Because this is a strong acid, we're going to assume that it is close to 100% ionized, 100% on the product side. Okay. We do have a equilibrium constant. Right now we'll call that Kc. It's going to be based off of the concentrations of products over reactants. We don't have any coefficients, so there are not going to be any exponents, but you know that if there's a 3 here as a coefficient, you would cube it, cube the concentration. So here we have H3O plus times the concentration of NO3 minus. What do we have in the denominator? Just the aqueous. You don't use liquid in the equilibrium expression. Concentration of H and O3. So that's the equilibrium constant. This has a special name because if you are studying acids in aqueous solutions, we would call this equation Ka. But it's the same thing as Kc. It's just that it's a special Kc because it's applying to an acidic solution. This is the acidity constant. Every acid has a characteristic Ka value, and again, equilibrium constants are temperature dependent, so most likely they would say this is a Ka at X temperature. Is there anything else I want to say? Let us make this into a general equation though, okay? So we could apply this equation to any acid. An abbreviation for acid typically is HA. And you'll see why in just a moment why we choose the letter A. But you can imagine this H is the proton that's going to be donated. Okay, plus water. I'm not going to put the phases here. H3O plus. And when you lose that hydrogen, or more specifically the proton, you're left with the conjugate base. And when you lose that proton, you drop in charge. You become more negative. A minus. It's A minus A because it stands for anion. But we also know that anion as what? We know it as the conjugate base. So this is the acid. So this is generalized, right? We don't know what the A minus is. In the first case, it was nitrate, and it was protonated at the beginning, so nitric acid. Anyway, we have the acid, we have the base. You know, the acid becomes the conjugate base, and the water, which is the base, becomes a conjugate acid. What was the purpose of generalizing this acid-base equation? Is to get us a Ka expression where we could substitute now any acid. So we are concerned about, let me write it out first and collect my thoughts. A minus, like some anion, divided by HA. When you have a Ka, you are specifically looking at one proton of the molecule being donated. I don't want to get too deep into this. We'll see some examples later, but if you have a diprotic acid, you'll have a Ka1 for the first proton and a Ka2 for the second proton. So we're always, in each case, generating one molecule of H3O+. Now the other thing I want to say, and let's set that aside, the other thing I want to say is that these are concentrations at equilibrium. So I could ask, what is the concentration at equilibrium if I dissolve an initial concentration of HA? Again, this will come later when we start to do problems, but we are headed towards ice tables to figure out X. Okay. Anyway, let me just put a reminder here that this is these concentrations at equilibrium. And let's put a box around this. This is your Ka expression. Okay, a caveat. Because we have a strong acid, HNO3, our denominator actually gets closer and closer to 0 because all of this essentially dissociates and we have none of the starting acid and everything is the H3O plus and the NO3 minus. So you can imagine that the numerator gets super large, the denominator gets super small, Ka skyrockets. So for HNO3, which is a strong acid, and it's one of the 7, right, that I asked you to memorize, one of the 7 strong acids, you assume around 100% ionization. As you get to 0, that Ka becomes infinity. So I'm going to say here that for strong acids, you don't normally see a Ka reported for strong acids. Ka is essentially meaningless, or we could say useless, or not used. So for strong acids, we assume 100% ionization. Therefore, Ka is not really helpful. You know where Ka is helpful? Ka is helpful for weak acids. Topic A is for strong acids. Let me show you an example with weak acid. So we're going to call this Ka for a weak acid. Okay, I don't know. If you look up the if you look up the Ka for nitric acid, I don't think you're going to get a number, or they're going to leave it blank. But we can get Kas for weak acids, and I'm going to choose a weak acid that's very similar, HNO2. HNO2 is a weak acid. Okay, HNO3 is a strong acid. HNO2 is a weak acid. We have this as aqueous, same deal, dissolve in water. You're going to create, not a lot, but you're still going to create some hydronium plus the anion. In this case, now it's NO2 minus aqueous. Okay. When I looked up this acid, well, this is nitric acid. Do you remember your naming, your nomenclature? This is, oh boy, this is nitrite, the NO2 minus, and then nitrites become us. This is nitrous acid. Anyway, I looked it up, and the Ka equals tiny, 4.5 times 10 to the minus 4. No units, okay? What that means is that what? You have very little product. You have very little H3O plus, NO2 minus, and most of your nitrous acid stayed associated. The H did not separate from the NO2 because that's such a small number. Now, let me think. Okay, I'm not going to do a problem using this Ka, not in this video, but in a future video. What could we do? Let me just give us a little preview. In the future, we can do what? We can calculate the pH of a solution if given the initial concentration of the acid and we'll say the weak acid, and its Ka. In the future, we are going to do ice tables. Going back to the ice tables that we saw in Unit 7, equilibrium. Okay, but I don't want to do that here because I want us to compare Ka to Kb. Because what if we're not dissolving an acid? What if we're not dissolving nitric acid to make the water acidic? Or we're not dissolving nitrous acid to make the water slightly acidic? What if we're adding a base? Whenever you're learning about a situation where you have to add a base, always have ammonia on your mind. We're going to look at Kb. That's called the basicity. I spelled it wrong already. Basicity constant. Let's use ammonia, okay? That's a very good base, whether you need to demonstrate a phenomenon in general chemistry or even organic chemistry. Use NH3, a neutral base. Anyway, what's going to happen? We throw this into water again. But now, instead of getting hydronium, what are we getting? That's the base that accepts a proton from water. And we know that, you know that when you gain a proton, you become more positive. NH4 plus aqueous plus what? Now we don't have H3O plus. Water is now the base. Oh, sorry, water is now the acid. It donated its hydrogen or its proton, and we get OH minus. See the difference? We're not getting hydronium anymore. Since we added a base, we're getting NH4 plus, and it's what is this? The conjugate base of water. So let's label. Test yourself. See if you could label the acid, the base, the conjugate acid, and the conjugate base. This is the base now. This is the acid. That base became the conjugate acid when it obtained a proton. And that acid, when it lost a proton, becomes the conjugate base. Now the thing is, we don't use Ka, right? Ka is telling me how much hydronium I have in comparison to the other components of the reaction. We're using Kb. Okay, so I could write the Kb expression for this equation here, but why don't I generalize it just like we generalized the acid as HA? How do we generalize a base? We'll call it B for base, and we'll have it neutral, just like ammonia, plus water. Okay, that's liquid again. It doesn't belong in the equilibrium expression. And what happened to our base? Our base obtained a proton and became more positive. We could demonstrate that or show that with BH plus or HB plus. It doesn't matter to me. Plus OH minus. That is consistent with our reaction. This is the expression that you want to put in a box. BH plus OH minus divided by the original concentration of, no, not the original, the equilibrium concentration of the base. Again, this is at equilibrium. Okay, let me make sure I have everything I need. Okay, before we leave this video, I'm curious. It seems like eventually we're going to be able to do problems where we calculate the pH of a solution if we're given the initial concentration of something, in this case the weak acid, and its Ka. Would we be able to get the pH if we're given the initial concentration of base and its Kb? Is it possible to calculate pH again, a question mark, if given the concentration of base if given the initial concentration of base, and it doesn't make sense to give the Ka for a base. You have to look up or be given the Kb. And the answer to this is definitely yes. The strategy. Again, we're not showing you this explicitly, but let me remind you, if you could do an ice table and you have this number and you have x, right? You could figure out the plus x and the minus x, okay? And you have the initial concentration. Do the ice table to figure out what x is. So you do ice, you get the concentration of OH minus, actually, because it's right there. And then you convert to, there are a couple ways we could do this. We could convert to POH, and then do 14 minus POH equals pH. And that's how you're going to get pH. You go through the POH. That's easy. Or if you know that you are at 25 degrees Celsius, you go through that equation, the Kw. Hydroxide concentration times hydronium concentration equals 1 times 10 to the minus 14. Okay. And we're getting this. Where are we getting this from? We're getting this from this equation here. Okay. I don't want to belabor the point. I think it's more useful if we just do a practice problem. I have one more video before we start doing a lot of practice with these equilibrium constants. Just to remind you, we have Ka, we have Kb, and in the previous video we looked at Kw. The next video we're going to relate all three of those, Ka, Kb, and Kw.